In the rugged mountains of Laos, I witnessed thousands of workers digging through nearly 200 kilometers of rock to construct the Vientiane-Bhutan Railway. This project stands as the largest infrastructure endeavor in the history of Laos. What is particularly striking is that over 62% of the entire route navigates through tunnels, bridges, forests, mountains, and isolated construction sites. The challenging terrain posed significant difficulties for the construction teams. Ultimately, this railway symbolizes a major achievement in modern engineering amidst Southeast Asia's toughest landscapes. In this video, I joined Datascope to explore how engineers built a modern railway through a challenging landscape. For decades, Laos stood as one of the most difficult countries in Southeast Asia for developing a logistic system. The country lacks a coastline and is characterized by rugged mountains. Dense rivers and streams further complicate transportation, which has primarily relied on roads. I delve into the innovative solutions that made this railway project possible. Transportation costs in Laos have consistently been high, leading to the construction of the Vientiane-Bhutan Railway, the country's first electrified railway. This railway spans over 400 kilometers, connecting Vientiane to the Bhutan border near China, and was developed as part of China's Belt and Road Initiative. The project, which required a total investment of $6 billion, constituted nearly one-third of Laos' GDP at the time, with funding sourced from Laos, China, and loans. It represents the largest infrastructure project in Laos history and aims to shift the country from being landlocked to land-linked. The construction faced significant challenges due to rugged terrain, necessitating the creation of temporary access roads for transporting materials to remote sites. I witnessed hundreds of kilometers of service roads being opened through the mountains and forests. Large bulldozers and excavators dug into the mountainsides to create narrow routes along the cliffs, where the road was only wide enough for a single truck. In some areas, residential communities had to be relocated to ensure safety due to the risk of landslides during mountain tunneling. I observed that many once quiet mountainous regions transformed into massive construction sites operating day and night, filled with the sounds of heavy machinery. This construction crossed the railway's total length of more than 400 kilometers, with up to 198 kilometers running through mountain tunnels. Nearly half of the railway was constructed on challenging terrain, necessitating the use of traditional drilling and blasting methods in hard rock mountain sections. I began the process by positioning drilling rigs near the tunnel face, where drill bits would create deep holes in a pre-calculated pattern. The precision of each hole's position, depth, and angle was crucial for determining how the rock would fracture upon detonation. After drilling, I placed explosives and detonators into each hole, ensuring the entire area was safe before detonating the charges. Post-explosion, excavators and hydraulic breakers were employed to remove the broken rock from the tunnel, clearing the path for further construction. After removing the loose material, I had to immediately reinforce the tunnel roof and walls. I first installed a layer of steel reinforcement mesh on the rock surface. Then, I applied sprayed concrete to lock the cracks in place and create a temporary protective layer. Next, I added a second layer of steel mesh in sections with weaker geology before applying another layer of sprayed concrete for increased stability. Ultimately, I continued drilling anchor holes deep into the surrounding rock mass to connect the sprayed concrete layer with the solid bedrock, enhancing the tunnel's stability. After the inspection was completed, I witnessed the cycle of drilling, blasting, rock removal, and reinforcement continuing meter by meter until the tunnel broke through the mountain. In certain sections of the tunnel that were long and straight with favorable geological conditions, I saw engineers using tunnel boring machines, TBMs, instead of manual methods. A TBM is a massive machine that can exceed 100 meters in length and functions as a mobile tunnel factory within a mountain. At the front of the TBM, there is a circular cutter head equipped with hard steel cutting discs. As the cutter head rotates, it effectively crushes and cuts the soil and rock ahead into smaller fragments. Unlike the blasting method, I use a TBM that advances continuously by applying pressure and utilizing the rotating action of the cutter head. As I crush the rock and soil, the material is efficiently transported backward with conveyor belts or a specialized system. This method allows for a steadier excavation process with reduced vibration, making it ideal for precision-required tunnel sections. After moving forward a designated distance, my TBM's internal systems position precast concrete segments for tunnel lining. Once assembled into a circular ring, I ensure the joints are tightened and grout is injected to securely bond the structure with the surrounding rock and soil. The biggest advantage of a TBM is its stable construction speed and high level of automation, allowing for continuous excavation, material removal, tunnel lining installation, and alignment control. However, TBMs require extremely complex preparation work, making them suitable only for longer tunnel sections that justify the high installation and operation costs. Many sections of the Vientiane Railway needed excavation through mountains, while others continuously crossed deep valleys, large rivers, and streams. This challenging terrain necessitated the construction of hundreds of bridges and viaducts along the entire route. Ultimately, the use of TBMs presents both significant benefits and substantial logistical challenges in specific environments. At the designated railway bridge locations, I oversaw the use of giant pile drilling rigs to drill deep into the bedrock. Steel reinforcement cages were then lowered into the boreholes, followed by high-strength concrete being pumped in to form the foundation piles. Once the foundations were completed, I witnessed the bridge piers beginning to rise. In certain areas, we had to disassemble equipment into smaller sections for transport and then reassemble it on site. Additionally, massive pre-cast concrete girders were produced in advance and lifted into place by heavy-duty cranes. For larger bridges crossing deep valleys, I often used the balanced cantilever method, building smaller girder sections symmetrically from both sides of the pier. When the final two girder sections met in the middle, they completed the closure segment, locking the structure into a continuous span. This system of viaducts helped maintain a lower gradient and stable curve radius for high-speed operations through Laos's rugged terrain. After completing the mountain tunnels, viaducts, and railway foundation, I transformed the site into an electrified railway system, starting with the installation of the track system. I laid ballast stones and layers for a flexible base, placed concrete sleepers, and erected thousands of electric poles along the line to supply power to the trains. I observed that the trains utilize a pantograph for electricity instead of traditional diesel locomotives, which enhances noise reduction and acceleration for high-speed transport. All associated infrastructure, including ticketing areas and freight logistics, was completed simultaneously with the railway's construction. Once the infrastructure was finalized, the railway began trial operations, with Vientiane Station emerging as the largest transport hub in the system. The modern design of many stations stands in stark contrast to the mountainous backdrop, highlighting the advanced technology of the electric trains. The total construction cost of $6 billion marked a significant investment for Laos, leading to a rise in the public debt-to-GDP ratio exceeding 100% during financial strains. The ownership structure of the railway project highlights its strategic importance, with 70% owned by China and 30% by Laos. Most funding came from loans provided by the Export-Import Bank of China, raising concerns about Laos' financial stability due to heavy debt. Critics believe that such large-scale projects may increase financial dependence on China, especially under the Belt and Road Initiative. Supporters argue that given Laos' economic size and terrain, options for financing a modern railway are limited. For China, the Vientiane Railway is not just a transport project, but a crucial part of its development strategy and the broader Belt and Road Initiative across Asia. I see the railway as a logistics corridor that enhances connections between China and Southeast Asia, reducing reliance on sea transport. For Laos, this modern electrified railway provides its first direct link to the international logistics network, significantly boosting the tourism industry by cutting travel times. I recognize that this railway is more than just a transport line. It represents a strategic infrastructure shift that could reshape regional trade and supply chains for decades. Building the railway required immense effort, including opening roads, excavating tunnels, and constructing bridges, transforming Laos' geographical destiny. However, with a substantial cost and debt, the success of this project hinges on whether it can effectively attract trade and investment, making it a critical test for the country's future.